E-learning presentation on axial modes in laser. Um, First of all, for obtaining lasing or to produce laser energy, we need an active medium. And this active medium could be a collection of atoms, molecules, gas, liquid, or solid. We have to excite this volume of material using energy of some form, and this process of exciting the material is called pumping, and the energy, of course, could be in the form of electricity, light, or even a chemical reaction. So when these atoms and molecules are raised to an excited state, the matter then relaxes, producing radiation in the form of photons, giving out laser light, say, or non-radiatively producing heat. And of course, this happens via phonons. So the active medium actually serves to amplify the radiation as it propagates through the active medium. So in order to sustain this amplification, but to sustain the release of radiation, we need positive feedback. And to make conditions suitable for positive feedback, an optical cavity is needed. So in this optical cavity, we have to have some form of a standing wave inside the cavity. So you need mirrors to reflect the radiation back and forth. So this back and forth movement of the material in the active material in the laser cavity produces axial modes. So the longitudinal modes or the axial modes of the laser are determined by various factors, and then these include the geometry of the resonator itself, and the reflectivity of the mirrors at either end, the properties of the active material, and inevitably the losses in the resonator. And these losses, as we'll soon find out, are important in determining the gain of the laser. So just as in the normal modes in classical mechanics or Schrodinger's equation solutions in atomic physics, we have a standing wave that extends from one end of the active cavity to the other, and where L subscript opt is the length of the optical cavity, and M is the number of nodes in the cavity. Lambda gives us the wavelength. So let's go to the next slide, and here we have, so if you have nodes at either end of the cavity, the number of wavelengths is obviously half, because this is half a wavelength and the other half goes this way. So for various values of M, you would have various axial modes in the optical cavity, and of course here this is the length of the optical cavity, as you would have noted. So these several axial modes are spaced at identical intervals given by delta nu, where nu stands for the frequency, and of course C stands for the celerity or the speed of light. And if we divide this by 2L, the length of the optical cavity, we can determine the number of the axial modes. So just a bit of recap, that the frequency is equal to the speed of light divided by the frequency, divided by the wavelength, lambda. And we use this formula for our laser. So if lambda subscript p is one mode, and lambda subscript p plus is one mode to the right or to the left, the difference in the frequencies or the axial mode spacing of the resonator is given by C over 2L. And the wavelength spacing can also be determined, and this is a lambda resonance equals lambda delta resonance equals lambda squared over 2L subscript opt. And of course, these several axial modes in the laser have a envelope which is called the grain, and the dotted line determines the threshold power. So the losses of the resonator have to be in excess of the have to be exceeded by the energy of the active medium in order to surpass the lasing threshold. And the gain profile and the laser threshold therefore select out the active axial modes, and they're shown in red in this diagram. And so the gain profile of the active medium is related to the number of axial modes at which the lasing occurs, and in this diagram they are 16 in number. And this ends my presentation. Thank you very much. Bye.